So let's have a look here at a bit of information. Now, this is right out of the notes. It's on page 110. And this is one reason why I have the notes. I just don't want you to have to be writing all this stuff down. It's not a real efficient way to learn. Okay, so let's kind of start at the top. This is an engineering class, okay? Up till now, you've probably had Engineering 111 and 112. It might have been a little while. You've had probably a good bit of math. Probably might have started physics and chemistry. That's science, okay? And math. That's different than what we do, okay? I'm an engineer. I think like an engineer. If my bridge is not theoretically correct, that's okay as long as it stands, okay? I'm focused very differently than a mathematician or a scientist. I'm thinking about how am I going to get this done and will it work? That's what I'm thinking about, okay? And that affects a lot of things in this class. All right. One thing it affects is significant figures. If you've taken chemistry, you've probably dealt with significant figures, I would imagine. In here, I've got one rule of significant figures, and my rule on that is use 3. Okay, that'll be fine for structural. I don't care whether I'm using significant figures if I'm making a large building like this. It doesn't make any difference. If I use 3 significant figures, I'm fine. Okay, we're done. Okay. Now the next thing is, there is a way that sometimes scientists and mathematicians express numbers. A mathematician likes a number like 4 pi because that's an exact answer. That's theoretically correct. I can't tell a surveyor to lay out a line 4 pi feet long. They're not going to like that, okay? Not at all, all right? So I want to use a number, and I want to give them a number. Now, if I take 4 pi, and I hit it on my calculator, what I get is 12.56637.061. Now what happens if I tell a surveyor to lay out a line 12.56637.061 feet long? What's going to happen? It kind of depends on the situation. If we both work for the same company, they might throw something at me, okay? Because that's not a very practical thing to do. If they work for a different company, they'll say, sure, I can do that, but I'm going to send you a very large bill to do that, okay? So that's not a practical answer. What I want is 12.6. I don't want 4 pi, nor do I want 12.56637.061. For an answer, I want 12.6. If you want to call it 12.57, that's okay. 3 or 4 significant figures, but don't give me 8 significant figures. And don't give me pi and things like that, and E and stuff like that. Those aren't numbers I can build stuff with. You with me there? Okay? A little different mentality here in how we look at things. I just want to kind of call that out. Okay? Mechanics. Okay, we're gonna look at objects at rest, which is statics. Some of you will also take dynamics, which is objects in motion. The two together are called mechanics. Okay? Okay, some basic definitions here. A mass is amount of atomic material. Okay, it's how much stuff I've got, how much atomic material I've got. A force is a push or a pull. Weight is a force that's caused by gravity. Okay, mass is measured in kilograms and slugs. Kilograms you've probably heard of because of all the science you've done. Slugs maybe not. That's an English unit. Okay, that's the English unit of mass. Now, where do they still use English units in the world? We use them here a lot. Structural engineering is done in pounds. That's how it's done. Also, they use English units in Liberia and Burma. Okay, they don't use them in England anymore. They don't use them in Australia. But we're such a large portion of the world economy that it's still a very viable unit system here, and we're very slow to change. Now, someday I think we'll be on the metric system, but not yet, okay? So I'll give you problems in both systems of units, because if you work in structural engineering, you're going to be dealing with pounds and kips and things like that. Okay, acceleration is a change in velocity. Okay, that's measured in meters per second in metrics, feet per second in the English are called imperial system. G is the acceleration caused by gravity on Earth. G is 9.81 meters per second squared, or 32.2 feet per second squared, which is feet per second per second. Okay? Now, most of the problems we deal with here are going to be on Earth, so those are numbers that we want to be familiar with. Okay, 9.81 and 32.2, just depending on which unit system we're in. All right. I've got G on your formula sheet on the right-hand side near the bottom. Now, these things are all related. There is an equation developed by Newton, Isaac Newton, F equals ma. The force with which you push or pull on something equals the mass times its acceleration. There's a corollary to that, another form of it that's used for weight. Weight is equal to mass times gravity. So the weight is a type of force. The acceleration due to gravity is, of course, a type of acceleration. So if I know mass, what I can do is multiply it by the acceleration due to gravity to get the weight. So 1 Newton is 1 kilogram meter per second squared. 1 pound is 1 slug foot per second squared. Those are the essential relationships there that we use. Okay. Okay, a particle is a body whose size can be neglected. It can be treated like a point mass. The motion of a pool ball can be could be done by using particle analysis. An analysis of the Earth and its orbit, that could be done using particle analysis. It really doesn't have to do with the size of the object so much as how you analyze it. Okay? Other objects in this class, anyway, we will consider to be rigid bodies, meaning they don't deform. It's an object whose parts, which we sometimes call members, do not deform or move in relation to each other. Okay. We have a concentrated force, which is a force acting at a point, like a guy wire, a wire pulling on an object. Distributed force is a force acting over an area, like a wind load or a snow load or something like that. Okay. The last thing we have here that on this front page is a safety factor. That's a factor that magnifies the design force. Okay. Because you see, when you're doing the problems in here, I will tell you what the forces are. And when you look at a textbook, it will say the force is such and such. It is 500 newtons. It's 300 pounds. When you start working, you're not going to know what the forces are. And you're going to have to guess. All right? Okay, now, if you're very confident in your guess, you might use a lower safety factor. If you're not confident in your guess, if you're not confident in how well the object is made and how sound the materials are and how it's going to be used, you will start using a larger and larger safety factor. What a safety factor does is it makes the actual design load bigger. It's usually a reflection of two things: the confidence you have in your design and the problems that you will have if the object fails. Okay? So this building was probably designed with a safety factor of about 1.5. This is designed to take 50% more than the actual loads they think it's going to have to support. That way, if they didn't mix the concrete quite right, if they didn't anticipate something in design, you know, they're doing okay. All right? That's what a safety factor is. Now, you know, in this particular example, failure of a building is just a horrible thing, right? You don't want that to ever happen. So you're going to have a safety factor that's large enough to prevent that, okay? If I'm designing I don't know, a pencil or something, they probably don't have too big of a safety factor on the lead, because if the lead breaks, well, okay, no one's too worried about that, okay? All right. So if I have a 200-pound weight, that's what I'm assuming the load's going to be, is 200 pounds, and I have safety factor 1.5, I'll design the object for 300 pounds is what I'll do. Okay, so that's just a run through that front page. Okay. And that's also a reminder of why you want to get a copy of the notes and bring them to class every day. I don't want to spend an hour going through this stuff and having you write it all down. That's not efficient, okay? I just write it down for you. We good with that? Okay. All right, let's have a look at an example here maybe. Let's say we've got a space vehicle and it has a mass of 135.2 slugs. And I don't know if I have this in your copy. You might have to just copy this one down, okay? Let's find a few things out about this. So let's say this thing has a mass of 135.2 slugs. That's a mass in the English system. Let's find out a few things about this space vehicle. Its weight in pounds and newtons, its mass in kilograms, its mass on the moon, and its weight on the moon. For conversions there, I've got a pound is 4.448 newtons, and the moon's gravity is 5.325 feet per second squared. We're doing all right with that? So what we're going to have to do is use the gravity to convert this mass into weight. We doing all right? Does everybody not have that down yet? Everybody good? Okay. So I'm going to use those equations that I had on the front page of your notes to do this with. I'm going to take the mass times gravity to get it into weight. So I know that F equals ma, so the weight equals mass times gravity. I know that G is 32.2 feet per second squared, which is 9.81 meters per second squared. Okay. So there we go. So I'm going to take the weight, which is 135.2 slugs times gravity. I'm going to use the English gravity, 32.2 feet per second squared. When I multiply those together, I get a slug foot per second squared, which is a pound. So that gets me 4353 pounds. I can then convert that into newtons. So that's the first two questions that I have, the weight in pounds and the weight in newtons. I use gravity to convert the slugs into pounds, and then I convert that into newtons. So we're doing all right with that? I'm just taking the mass times gravity. That gets me into pounds. When I take slugs times foot per second squared, I get a slug foot per second squared. That is a pound. Okay, they're equivalent. Then I can convert the pounds into newtons. 4.448 newtons per pound. We good with that? Okay. Anybody not have that down? Okay. All right. Now let's get that into mass. Okay. So what I've got, again, I got F equals ma and W equals mg. Well, mass is weight over g, weight over gravity. So I can take the weight in newtons and divide it by gravity. That'll get me this rather odd looking unit, a Newton second squared per meter, but what that is a kilogram. So I was given the mass, okay, of both of the, in English units, 135.2. I found the mass in the metric system, which is 1974. So now I've got the mass. Now what the mass is the amount of atomic material. That's not going to change. Okay? So the mass on Earth is also the mass on the moon. That does not change. Okay? But what happens when I take that mass up to the moon? What happens to the weight then? Yeah, gravity changes. The gravity on the moon is not so strong, so the weight becomes less. The mass does not change. The mass stays the same, but the weight changes with the gravity. Okay. Now, we're not going to do too much of this stuff on the moon when we're going through the class, but I just at least want to make you aware of this. Okay. The mass stays the same. The weight changes. You ever see the films from the people walking on the moon? They kind of hop when they walk because their muscles are built up for Earth, but they're in this really weak gravitational field, so they kind of bounce when they walk because their legs are so strong for what they need to do. Okay, we good? All right, so the last bit on this is find the weight on the moon. We just take the mass times the gravity of the moon. So the weight is quite a bit less on the moon. So I'll take the 135.2 slugs times the gravity on the moon, the 5.325, and then I'll take the weight, and then I'll convert that to newtons to get it into the weight on the moon. So the mass stays the same. The weight changes depending on what gravitational field you're in. So one thing to remember about what we're doing in this class is we work with weight and force. We don't really work with mass here much. If you have a mass, normally what you want to do is convert it into weight. Because we're going to sum up forces in this class usually. It's normally what we do. The other thing I'll point out is you notice I'm carrying probably 4 significant figures, sometimes even 5 here. I can cut it down to 3 when I report my answers, okay? So if you report in your answer, if you give me 4 or 5, I don't care. I just don't want to see 8 or 9 or 10. That's just getting a little ridiculous, okay? So you go 3, 4, 5, whatever, just something reasonable, okay? So if I'm going to answer that, if that's a homework problem, I'm going to put all those answers in one box like that, and now I've got to round it down to 3 significant figures. I can always round them back when I want to. Okay? You know, and again, if you kind of think of it from a common sense perspective, this building would not be designed any different for 4,350 pounds versus whatever that other one was. What was it? 4,000, I don't know what it was, but the other answer, right? At the level we're working at for structural type design, 3 significant figures is fine for what we do. Okay. So we're doing all right with that? Okay. So how about Friday? Let's do the statics project that most of you have turned in already. But let's also do a problem here just for fun. Let's do 112. Now 112 is on that handout that I gave you in class. It's also in the packet. You will need the packet for Wednesday, okay? But if you don't have it and you want to start working on it, it's on the back. It's problem 112 there, okay? And that's due Friday, and that will be the 10th, I think. There we go. So we doing all right with that?
Is this problem 112?
No, it's on the back. It's yeah, it's the second problem down. I've got like a list of problems.
This one? Oh wait, all right, yep. The commercial grade panel.
Yeah, it's that light fixture thing. The light fixture one. It's pretty straightforward. Yeah, we good? That's due Friday. And if you have questions on it, I'll take them on Wednesday. So normally I assign things 2 sessions out. So if you got questions, I can take them, all right? We good? Okay, and we'll see what we can do about the room. We'll just start looking into that. Okay. All right, so we're good to go.